Good morning, everyone. Today, we'll continue to learn how to use factor analysis. Factor analysis is a data reduction technique used to reduce a large number of variables to a small set of underlying factors. These underlying factors summarize the essential information contained in the variables. It's very useful. If you, in your future thesis research, if you use the survey questionnaire in your study, then the factor analysis is necessary for you to use. Here, I will show you how to use the factor analysis to reduce the variables. Let's look at the example here. Here, we collect data from x1 to x7. x1 to x7. Here, x1 is the income of state-owned economic units. x2 is the income of collective economic unit. So, we collect totally 31 provinces in China. Okay, so totally we have 31 cases. And we have x1 to x7, 7 variables. Okay, so here we want to compare the incomes of different districts, different area. Firstly, we want to reduce 7 variables to a small number of underlying factors. Step 1, we need to judge if factor analysis can be used. And then, second step, how many factors can be extracted. Step 3, we will name the factors. 4, then we will calculate the factor and compare different areas. Which area is the highest and which area is the lowest? First, let's look at step 1. To use the factor analysis, we will click Analyze and then look here, Dimension Reduction Factor. Okay, input all the variables into the variables and then select the descriptives. In descriptives, please select coefficients, KMO, and Barrett's test of sphericity. Continue. Extraction. Here, the default method is principal components. We will keep it. And also the extract method, the default, is based on eigenvalue. If eigenvalue greater than 1, then the factor will be extracted. Okay, so all of them we will keep. Next, rotation. Rotation is used to sometimes when the factor is extracted, it's harder to explain the factor, so we need to use the rotation technique. We will change the factor so that the factor can be easily explained. Rotation, normally, we will use the value max. So click here. Continue. Scores. After the factor is extracted, we need to use the one way to calculate the factor. So here is the way to calculate the factor. Normally, we would like to use the regression. Also, the regression method is a default method. Okay, and display. Select display factor score coefficient matrix. From this coefficient, you can write down the formulate to calculate the factor. Continue. Options. For missing value, if you have missing value, then replace with mean. So select replace with mean here. And coefficient display format, yes, please select sorted by size. Okay, yeah, then continue. Okay, here. Okay, here shows the desired output. Firstly, let's look at the correlation matrix. Correlation matrix, KMO, Bartlett, they are all used to help you to judge if we can use factor analysis for this case. Okay, so we use these two outputs. We can answer the first question, whether the original variables are appropriate for factor analysis. Okay, I'll copy it. Here is for the first question. Yes, investigate whether the original variables are appropriate for factor analysis. Okay. And then next is the KMO. First, let's look at the criteria. Here is the criteria. In this correlation matrix, if a considerable number of correlation coefficients are less than 0.3, then we can conclude that the matrix is not suitable for factoring. Okay, let's look at this. Correlation matrix. Okay, here all of them more than 0.5. Here, yes. After we check we can see that the smallest coefficient is 0.482. Okay, this is the smallest. Okay, and so that means most of the correlation coefficients are relatively high, or we can say that the correlation coefficients are more than 0.482, and most of correlation coefficients are relatively high. Variables show relative strong linear correlationship. So, common factors can be extracted. Factor analysis can be used. Okay, so from the correlation matrix, you can answer factor analysis can be used because there are relative strong linear correlationship among these variables. Okay, yeah. Next, let's look at the KMO and Bartlett test. Here, first let's look at the KMO. KMO is to analyze if the sample size is adequate. If the sample size is adequate to run the factor analysis. And the value of KMO ranges from 0 to 1. The closer the value of KMO to 1, the more adequate is the sample size to run the factor analysis. And the criteria of KMO value to judge if the sample size is adequate. 0.5, it means it can be accepted. If KMO more than 0.9, it's superb. 0.8 to 0.9, great. 0.7 to 0.8, good. 0.5 to 0.7, mediocre. If the KMO minus than 0.5, it's not acceptable. Okay, if it's less than 0.5, it means more samples should be taken for analysis. Okay, and here the KMO is 0.882. So that means the sample size is adequate to run the factor analysis. Okay, we have 31 samples and the sample size is adequate. Next is Bartlett's test of sphericity. The Bartlett's test of sphericity is to test if the correlation matrix is an identity matrix. Identity matrix means all the variables, they have no relationship. They are independent. But here, the significance of the Bartlett's Bartlett's test of sphericity, the significance is less than 0.001, right? So the hypothesis is not accepted. Hence, the correlation matrix is not an identity matrix. Okay? If it's an identity matrix, then the factor analysis cannot be used. If it's not an identity matrix, it means the factor analysis can be used. Okay, so from KMO, from Barrett's test, the conclusion is it can be concluded that the factor model is appropriate. So that means we can use the factor analysis. Factor analysis is appropriate to use. Okay, so number 1, we have analysis. Okay, number 2, how many factors can be extracted? We will answer this question. First question, we can use factor analysis. Second, how many factors can be extracted? Okay. First, let's look at the community. Where is the community? Here is the communalities. Okay, look at here, 7 variables. Think about the integer variable is 1. Integer means this variable, if this variable include 100% of its information. Here, the right is the extraction, right? Extraction means when we use the extracted factor, how many information can be explained by these factors? Here, it shows 0.76, so that means 76% of the information can be explained by the factor we extracted. Okay, so higher community of a variable indicates that the major portion of its valuability is explained by all the identified factors in the analysis. Okay, so here, the second, collective economic unit, integer 1, and the extracted factor can explain 85.1% of the information. Okay, so here, so it's very good. But let's look at here. Other economic units. Other economic units, the extraction is 0.592, and the associated economic units 0.599. So that means more than 40% of the informations of these two variables are lost. Okay, so it means the factor extracted is not ideal. It's not ideal. Okay. It can be used. Why? Because here is the criteria. Okay, if a community of variables is less than 0.4, it's considered to be useless and should normally be removed from the model. Okay, so that means if any of them, the communality is less than 0.4, then this variable should be removed from this model. Okay, but here all of them are more than 0.4. So that means we don't need to remove any variable from this model. Okay, remember here? Okay, however, the variables are, here we have two of them is less than 0.6. Okay, here is the 0.599 and 0.592. Okay. Yeah, here's nearly 40% information of these two variables is lost, right? So the overall effect of this factor extraction is not ideal. It's not ideal. So yeah, let's look at how many factors did we extract. Okay, let's look at here. Okay, so in this time, if we use the criteria, the integer eigenvalue more than 1, then the factor will be extracted. And let's look at the integer eigenvalue. The component 1, the integer eigenvalue is 5.331. It's more than 1. The second component is less than, is 0.568, which is less than 1. So this factor is not extracted. And then next, smaller. Okay, so here, according to the criteria, we just extracted the factor with the integer eigenvalue more than 1. Under this criteria, just one factor is extracted. Just one factor. Okay, and this factor, it just explain 59.9% of this variable. So we think it's not enough. We want to extract more factor. Okay? Can you understand? Okay, things, because okay, so since more than 40% information is lost, so the overall effect of this factor extraction is not ideal. If we extract one factor, it's not enough. So we want to change the criteria. We want to extract 2 factors. Why? Because if we extract 2 factors, then look here, the cumulative will be 84.259%. So that means 2 factors can explain 84.259% of the information of the valuables. Okay, so next we want to change the extraction value criteria. Okay, please look at here. Other things we will not change. We just change the extraction here. Now, here we want to extract fixed number of factors. Yeah, so please select here, fixed number of factors. Factors to extract, yes, please input the number 2. Now it's 2. We want to extract 2 factors. So here I input 2. Okay. So I want to change and then let's look at the output. Continue. Okay. Okay, the correlation matrix, the same. KMO, same. Communities. Let's look at the communities this time. And how many factors we extracted. Now, okay, let's look at the communities. Yeah, from here you can see that the communities of all the valuables is from 0.767 to 0.922, right? So that means most of the information of the valuables can be explained by the extracted factors. So that means this time the factor analysis is ideal. Okay, so that means we extract 2 factors is reasonable. Okay, I make it smaller. Okay, so let's look at here. Here is the total variance explained. Okay, now, because we input the number of the factors, the number of factors is 2. So the computer will help you to extract 2 factors. Here is number 1, here's number 2. And after 2 factors extracted, totally the sum of squared loadings is 84.259. T means total variance explained. Two factors together explain 84.259% of total variance. Okay, on the whole, the information of original variables is less lost. Hence, the effect of factor analysis is ideal. Okay, so that means, okay, two factors is good. So, number 2. Okay, so question 2. We solved. How many factors can be extracted? We can answer 2. 2 factors can be extracted, and these 2 factors together can explain 84.259% of total variance. Okay, the information of original variables is less lost. The effect of factor analysis is ideal. That's the conclusion of second question. Okay, third question. Please name the factors. Okay, so that's the first. Okay, I delete this one. Okay, third question is please name and interpret factors. 2 factors have been extracted. Yes, please give them name. Please name them and interpret the factors. So let's look at the unrotated factor solution. Here is unrotated. And then here is rotated. Here is factor 1. Here is factor 2. If the factors is not rotated, then look at here. All the upload of the variable. Here is upload. Upload is 9.955, and the factor 2 minus 0.9095. Factor, this is variable, the number 2 variable, the variable 2. And the component 1 is here is 0.923. So when you compare these 2 rows of data, you can see that all of these coefficients in component 1 is more than their coefficients in component 2, right? So it's really hard to explain, to name the component 2, because component 1 include most the majority of the variables. Okay, so it's hard to name the 2 factors. So we need to rotate. After rotate, here is the component matrix after rotate. After rotate, let's look at here. In component 1, associated economic units is the coefficient is the biggest, 0.883. Then joint stock economic units, 0.773. Next, collective economic unit, 0.720, and state-owned economic units, 0.702. Okay, so these 4 variables has larger upload in component 1, small in component 2. So we can say that the component 1 can be explained by these 4 variables. On the contrary, let's look at these 3 variables. Other economic units, the coefficient is 0.908 in component 2, 0.213 in component 1. So component 2 is bigger than component 1 for other economic units. Following invested economic units, also the coefficients in component 2 bigger than component 1. Hong Kong, Macau, and Taiwan economic units also has the big coefficient in component 2 than in component 1. So that means we can say that component 2 mainly can explained by these 3 variables. Okay, so we can use these 3 variables to name the factor 2. Or we can say component 2 or factor 2. Okay? Yeah? So, factor 1, other economic units, foreign invested economic units. Okay, Hong Kong, Macau, Taiwan. So we can call it, this is factor 2, sorry. So, all of these variables measure the foreign investment economic unit. Therefore, it may be termed as foreign investment economic unit. And the factor 1, sorry, I think here is internal and here is out. And factor 1, since it includes associate economic units, joint stock economic units, collective economic units, state-owned economic units. All of these economic units is the internal. So this factor can be named as internal investment economic unit. Okay, so here is the name. Please name the factor 1 and the factor 2. And for you will use the rotated component matrix to analyze. The factor 1 includes which variables? Factor 2 includes which variables? And you use these variables to name factor 1. Use these variables, use their common feature to name the factor 2. Understand? Can you understand? Okay, so here we complete step 3. Name the factors. Okay, next we will calculate the factor score. Okay, please calculate the factor score. So how to calculate the factor score? In fact, the computer automatically calculates the factor score for you. But still, you need to know the regression model to calculate the factor score. So please find the component score coefficient matrix. Look at here. Here is the component score coefficient matrix. And also you can write the regression model to calculate the factor score. Look at here. Component 1 is factor 1. Okay. Component 2 is factor 2. Okay, so we can write down the regression model to calculate factor 1. I told you component 1 is factor 1, and factor 1 we can use F1. F1 coefficient is 0.223, right? So it's 0.223 multiply state owned economic unit. Okay. Also, you can look at here, which is the x1, which is x2. Okay, so state-owned economic units. State-owned economic units is x1. Add 0.196 multiply collective. Collective is x2. Okay, and then add associate economic units x3 0.656. joint stock x4 at 0.331 multiply 0.4, then foreign invest x5 minus 0.062 x5. Hong Kong car at 0.02 multiply x6. Finally, other economic units minus 0.519 multiply x7. That's the F1, right? Okay. Then please write down F2. Okay, use the same way to write down. Minus 0.002. Second is 0.042. Third minus 0.504 minus 0.117. Okay, and then here plus 0.322. .244 and add 0.784. Okay, sir. According to the component score coefficient matrix, we can write down the regression model to calculate F1 and F2. Also, the computer already calculated the factor 1 and factor 2. Where are they? They are here. Yeah, I will delete these two, okay? Because I don't need them. Okay, so here is the factor 1, here is the factor 2. Okay? Okay, so here is factor 1, here is factor 2. Okay. Now, we complete the F1 and F2. F1, if F1 is more than 0, so that means in this area, the F1 is more than 0, so that means that the internal investment economic unit, their score is more than the average level. Average level is 0. Average level will be 0. Okay. So when we look at here, we can see that some of them is more than 0 and some of them is minus. It's less than 0. Okay, and you can analyze it. Analyze F1 and F2. And you can see that F1, F2, the mean is 0. The standard deviation is 1. Okay, so that means the mean of this F1 is 0. 0 is the average level. Okay, and if the F1, the data of F1, score of F1 is more than 0, it means it's higher than the average level. Okay, next. If you need to use just one score to comprehensive evaluate, then you need to combine this F1 and F2 into one score. Okay. So next, let's comprehensively evaluate the average annual income. So please comprehensively evaluate. Comprehensive evaluate means just use one score. Now F1, F2, we have 2 scores. F1 is the income of the internal investment units, economic units. F2 is the foreign investment economic units. Okay, so how about the average annual income of different province? Yeah, you are asked to use one score. Okay, so let's look at here. Please look at here. Look at the total variance explained. Okay. Copy this. Okay, sir. If we use the comprehensive evaluation, then we will use F. Look at here. F1 include 45.261% of variance. F2 include 38.997% of variance. Totally 84.259% of the variance, right? So F1 we can use 45.261 divided by 84.259. The cumulative. Okay, and then multiply F1, add F2, 38.997 divided by 84.259 multiply F2. Okay, then use this equation. You can calculate the comprehensive evaluation F. Okay, I write down it. Okay, then here, firstly, I will establish a F. Here, I would like to use F1. Here, F2. F is the comprehensive evaluation. So, establish the variable F first. Then, transform compute variable, target variable F, and then calculate F. F is 45.261 divided by 84.259 multiply F1, add 38.997 divided by 84.259 multiply F2. Okay, here we use this equation to calculate the comprehensive evaluation F. Okay. Now, we have the comprehensive evaluation F. Also, we have F1, F2, and F. Okay. Then next we will plot and we will compare. First, plot the scatter of two factors of different area. If factor score more than 0, it indicates higher than mean of all area. Yeah, I told you. Okay, so let's plot. Let's plot the scatter of two factors of different area. Okay, here. Graph, scatter dot, simple scatter. Define y. For example, F1 is y, F2 is x, set marks by area. Okay, set marks by area. Okay, and then, oh, sorry, it's not set marks. Label cases by area. Label cases by area. Okay. Now, we have the graph here, and we want to double click it. Here, please draw a zero line. Position, change it to 0. Okay, and then the y-axis, position 0. Okay, so you can see that this area 1, 2, 3, 4. These 4 area F1 more than 0. F2 more than 0. F1 more than 0. Right? So this is the rich area. And so here is there 1, 2, 3, 4. These 4 areas are developed area. And here, all of these areas, F1 minus 1 minus 0, F2 minus 0, it's developing area. And some of them, for example, this area, the F1 is very high, but F2 is less than average level. So it's unbalanced. Okay, let's look at which area are they. Yeah, please click elements here. Yeah, first click it, then element, show data labels. Okay, so here is Shanghai, here is Zhejiang. Yeah, the Zhejiang is our university location, the location of a university. Shanghai, Peking, Beijing. Okay, and here is Guangdong. Guangdong province, the internal investment economic units, their income is very high, and but their foreign investment economic units, the income is less than the average. Okay, so from here, yes, you have the information of the incomes of different units in various provinces. Okay, so here the information is useful. Okay. Then next, please draw the bar chart of comprehensive score of all provinces and analyze. Okay, so please draw a bar chart. Here is the procedure. Here is the output. Okay, yes, I show you. Here is the comprehensive evaluation, right? Graph, chart, legacy. Here is the bar, and simple. Besides simple, please select values of individual cases. Values of individual cases, okay? Please select here. Define. The body present F. Okay. Okay, but here we just have the numbers like this, right? So, yes, please change it. The variable, not case number. The category label, not case number, but the variable. The variable is the area. Okay, so here you can find the comprehensive evaluation of income in different areas. We can see that the Beijing is the highest. Also here, 0 is the average. 0 is the average level. The average income of all areas is 0. If the F, the comprehensive evaluation of income, is more than 0, then it means it's more than the average level. If it's less than the 0, then it means it's lower than the average level. Okay? Okay. If it's not very clear, so if we want to see the sequence of the area from the highest income to lowest income, then you can do it like this. Firstly, I would like to use the data and sort cases. Okay, sort cases. Sort by F. Sort order, ascending or descending. I think I would like to use descending from the highest to the lowest. Okay, then, okay, now, all the factors, all these cases, yeah, will be from the highest income to lowest income. Then, use the graph, the bar, simple, do the same thing. F, area, okay. Now, you can get a new plot. This new plot, the area is sorted by the income with a descent sequence. Okay, from the highest income to lowest income. So you can see 北京、上海、广东、浙江、福建、天津、江苏、西藏、海南、云南、新疆。新疆 is, look at here, 新疆is the average level. And here, these provinces, their income is higher than the average level. Also, you can find Beijing, Shanghai, Guangdong, these three provinces, or these three provinces has the highest. Their income is higher than other areas. And Beijing is the highest. Next is Shanghai, then Guangdong. Also here is内蒙古is the lowest. And then Shanxi, Qinghai, Heilongjiang, etc. Okay? Yeah. So this plot is clearer to show the income of the areas, different areas. I'll copy it. Okay, now this case is explained completely, hoping you can understand.